Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another session, and today we are doing quiz revision for the quiz on Tuesday. And the quiz on Tuesday is going to cover those two topics. It's going to cover the nature of force as well as the friction and gravity. Okay, so the way this is going to work is we're going to go through some questions, and inshallah we'll answer the questions together, and you'll get a better understanding of what to expect. Okay, so here is a question now. Let me just change this color. I don't like using red. If I can avoid it, I will. What do we call the force of gravity acting on an object? So obviously, any object here on Earth has a force that's pulling it down. So this force pulling it down is actually called weight, and it is caused by gravity, but the force itself is called weight. All right, so that's an easy one. Anything on Earth is the force acting down on anything on Earth towards the center of the Earth is known as weight. Okay, moving on. Now, what is the force opposing it? So let's say, for example, I have a table, and I have an object on the table, so this box. I've got weight acting down. What is the force acting up? Does anyone remember? It is known as normal force. So I've got normal force, and that will oppose weight. Okay? Remember Newton's third law, now this is later on, is for every action there is an equal and opposite reaction. So if we've got weight acting down, we've got normal force acting up. Riding on a bike on the road is an example of what kind of friction? What kind of friction is it an example of? Whenever we have a rolling object, mainly a wheel or a bearing or even a log that is rolling on a surface, this is an example of rolling friction. Okay? That is what that is. And of course, friction is measured in newtons. In case you had forgotten, friction is measured in newtons. Right, let's move on. Sailing on a boat on water is an example of, so we've got a boat that is going through the water, and that is an example of what? That is an example of what kind of friction? Okay, so some of you would have figured it out. It is an example of fluid friction. All right, so we've got this thing called fluid friction. What is fluid friction? Fluid friction is basically refers to any object that's moving through a fluid medium. So what is a fluid? A fluid is equal to gas or a liquid. Both of these things can be fluid. So if something's moving through the air, then we call that fluid friction. And if something's going through water, that's also fluid friction. So fluid friction refers to any object that is moving through liquid or gas. And I want you to remember at this point that basically friction is a force that exists between two objects. So it could in theory exist between a solid and a solid, but it also exists between solid and gas and solid and liquid. So all of these are forms of friction. So just because, like for example, you rubbing your two hands together, that's friction. That's a solid and a solid. But let's say if my hand is just going through the air, I'm also feeling some friction here. If I blow on it, I'll feel some friction. That is a form of friction known as air resistance. Now, if it's going through the water, that's known as water resistance. But all of that is, if it's going through water or if it's going through the air, it's known as fluid friction. A fluid is just any medium that can flow through pipes. So that is what we know as a fluid. What are the different types of friction? There are 4 different types of friction. 4 different types. So the first one is, I'm just going to start with the one we just did, fluid friction. We've got rolling friction, We've got static friction, which exists between two objects that are not moving. I'll explain these in just a minute. And we've got sliding friction, also known as kinetic friction or moving friction. Now, all of these are friction, all of these are forces, all of these are measured in newtons. Friction is a force, remember? So fluid exists with liquids, it also exists with air, right? So if a plane is moving through the air, it experiences air resistance. What is air resistance? Air resistance is fluid friction. Another example is a boat on the water, okay? Rolling friction exists between wheels and the road. So if you've got a wheel going on the road, any kind of wheel, so car wheel, a bike wheel, a skateboard wheel, any kind of wheel rolling on the road, that is a type of rolling friction. Static friction is what exists between an object and another object that stops it from moving. So here's an example. I've got one of my favorite books, my physics book, and I've got my phone on it. And as you can see, it's not going down, even though it's on a pretty steep incline. What's holding it in place is static friction. Now this here is made of leather, and leather is a bit like rubber. It's got a high coefficient of static friction. So as I'm moving it down, it's actually not moving. Now it started moving. So that is a form of static friction. So static friction is the friction that exists between two objects that are not moving. Okay, so when it's not moving, that's called static friction. And sliding friction is what exists between objects that are sliding past each other or moving past each other. So I'm just going to take that same example with the block, but now this time the block is being pushed. So as long as the block is being pushed, say for example I'm putting my hand over here and I'm pushing it with my hand, okay, and I'm applying a force, as long as it's being moved, then that's called sliding friction or moving friction. So four different types of friction. Fluid friction, which is through the air or the gas and water. Rolling friction is when with a wheel or anything circular that's rolling on top of a surface. Static friction is when the object is not moving, what's holding it in place. And finally, we've got sliding friction, which is what we have when an object slides past another object. What is the difference between mass and weight? That's another good one. So here's a person, and they are, you know what, I'm just going to draw a smaller person. Here's a person, and they are standing on the earth. Right, so here's the earth. And obviously there is a force pulling them down. That force pulling them down, we know that as weight, which is caused by gravity. So at this stage, if you refer to that force as gravity, that is acceptable. Now, that person has a mass. So let's say their mass is 50 kilograms. Remember, mass is in kgs, so mass is in kilograms, while weight is a force, so it's measured in newtons. Okay? So I've already told you a difference between the two. Mass is measured in kilograms, while weight is a force, so it's measured in newtons. Now, here's the thing. So this person has a mass of 50 kilograms, but their weight is 500 newtons. Why is that? Because their weight has to do with where they are. What does that mean? If they are on Earth, their weight is going to be 500 newtons. If they're on the moon, their weight is going to be approximately 1/6 of that, which is about 80 newtons. If they're in outer space, their weight is zero newtons. Now, that might sound a bit strange. How could they be 0 newtons? Well, remember, their mass is different. Their mass in outer space, let me just draw them kind of floating. Here they are floating in outer space. Okay, like Superman, and they are at this stage, because they're in outer space amongst the stars and the moon in the distance, when they're in outer space, their mass is still 50 kilograms, but their weight is suddenly 0 newtons. Why is that? Because weight has to do with the pull of gravity. Weight has to do with the pull of gravity. There is no pull of gravity, so they feel weightless. They feel weightless. It means they feel like they have no weight, but they still have the mass. Mass is the amount of matter. That's what mass is. Mass is amount of matter. That means blood, guts, bones, cells. That's your mass, okay? That doesn't change. If you're on Earth, if you're on Mars, if you're on the moon, if you're in outer space, that doesn't change unless you do a diet, okay? Is the amount of matter. However, weight is a force due to gravitational pull. That means the pull of gravity. So it depends on where you are. Sometimes there's no gravity. If you're in outer space, there's no gravitational pull, so you can be zero gravitational pull. Okay, so I hope that's clear. Your mass stays the same, your weight changes. Your mass stays the same, your weight changes. Your mass is measured in kilograms, your weight is measured in newtons. Your mass is the amount of matter that's inside you. It doesn't change wherever you are. Your weight changes depending on the gravitational pull. If you're on Jupiter, it's going to be much higher. If you're on Earth, it's going to be about 9.81 per kilogram or 10 newtons per kilogram. 10 meters per second squared per kilogram. And it's going to, if you're in outer space, it's going to be zero. So that is the difference between weight and mass. What factors affect friction? Interesting. Okay, I'm going to do something here, and you absolutely don't need to know this. Okay, you do not need to know this. One more time, you do not need to know this. This is the friction formula. Okay, it's okay is equal to mu sub S or K, depending on whether we're talking about static friction or kinetic friction, multiplied by the normal force. Okay, that is the formula for friction. Right. Now, as you can see here, this here is dependent. This is the coefficient of friction, and it depends on the material. So every material has its own stickiness, its own friction. So rubber is different to glass, is different to metal, it's different to wood, it's different to ceramic, it's different to tile. All of these materials have their own friction. Now, the other thing as well is the normal force. And let me explain what this means. Remember how we said weight acts down, and then there is something opposing weight. What is that? The normal force. So that has to do with weight. But what does weight have to do with it? Let me explain. So you've got different materials. So here I've got sandpaper, for example. And over here I've got newspaper. So the material makes a difference, but let's also talk about um, how the gap is between the material and the block. So let's say, for example, I'm going to take all of this off. So we know the material makes a difference. Okay, if you're wearing rubber shoes or if you're wearing socks, we know the grip is different. That's obvious. Now, let's have a look. What if I have a piece of wood sitting on this tabletop? Now, there is a gap here, right? Now, what happens if the gap is quite large? If the gap is quite large, the friction is going to be less. If I zoom in, this is what this looks like. So here's the piece of wood, and here is the table. And if the gap is quite large, the friction is less. Now, what happens if I add some weight to that? So I'm going to add some weight on top of this block. I'm going to add some mass, I should say. What's going to happen to the gap? Now, what happens to the gap? Watch this. What happens to the gap is obviously the gap is going to get a lot narrower. What is that going to do for the friction? It's going to increase the friction, isn't it? It's going to make the friction larger. So basically, if you add more weight or squeeze it together, then the gap is going to be less, and therefore those surfaces are going to rub together a lot more, and the friction is going to be higher. So what factors affect friction? The material, the type of material, and so that's one. Number two is the size of the gap, the size of the gap. Okay, and that is due to the weight force, or how much force is on top of the object, forcing it to be in close contact with the surface. What factors affect the force of gravity between objects? Now we're talking about something else. So if I've got, remember what we said, any object with a mass has gravity. Anything. So basically, let me just use a different color because I get bored of one color. Here's a feather, and feathers are very, very light. And here is a bowling ball, and that is relatively heavy. And here is an ant. And ants are quite light. But turns out all three objects have their own gravitational pull. So this has its own gravitational pull, this has its own gravitational pull, and this has its own gravitational pull. Why is that? Turns out, so this is one of the laws of creation. Allah subhanahu wa ta'ala created us this way. So anything with a mass has gravity. Anything with a mass has gravity, whether it's a feather, whether it's a bowling ball, whether it's a person, whether it's a planet, whether it's a moon. But of course, the gravitational pull of something relatively small, like a person or a feather, is going to be really, really tiny compared to a planet. Here on Earth, we don't really feel the gravitational pull from anything besides the Earth. Okay, and so if I let go of this pen, it falls down. Why is that? Gravity is pulling it down. The Earth is pulling it down. Now, however, there is gravity for every single object. So including the bowling ball, including the feather, including the ant, including the pen, including anything with a mass, okay? So now knowing that, here's the question. The question says, if there is gravity between different, if there's gravity for every single object, then there must be a pull between different objects. And yes, there is. So if we take, for example, the sun and the earth, there is a pull between the sun and the earth. The sun pulls the earth and Mercury and Venus and Mars and all the other planets. And that's why they kind of circumvent the sun. So there is an attraction between objects. Okay, so knowing that, what is the attraction between those two objects? Or what is the attraction between the Earth and the Sun? What determines the attraction between a planet, so here's a planet, and say the Sun? What determines that? What determines that attraction? Okay, and what determines that attraction is, once again, I'm going to write a formula, and this is not for the quiz by any means. This is just to help me explain it. So there are three laws of motion, but some people say there are four. And the fourth one, the unspoken law of motion, is the law of gravitation. And that is this law here, G multiplied by m1, m2 over r squared. As you can see here, so G is a constant. We don't have to worry about that. But what does the m stand for? M stands for mass, and r stands for distance. So some of you clever cookies would have actually figured it out by now. There are two factors that affect gravitational pull between objects. Two factors. First one is the mass of the object. Mass of object, as you can see from the formula, the mass of the object, mass of object 1, mass of object 2. And the other one is the distance between the objects. Distance between objects. So what does that mean? What that means is objects. Objects. What that means is this. The bigger the object, mass-wise, the more massive it is, the more mass it has, the more massive, the more gravitational pull it has, right? So a planet like the Earth has a lot of gravity, but a planet like Jupiter has bigger gravity, and the Sun has even more gravitational pull. The Sun's gravitational pull is approximately 1 million times that of the Earth, because it is 1 million times bigger than the Earth. What about the Moon? The Moon is 1/6 the size of the Earth. Well, guess what? It's 1/6 the mass. Turns out it's 1/6 the gravity. Interesting. Okay, so the mass and the distance. Well, let's talk about distance. Turns out the closer you are to an object, the more the gravitational pull is going to be. That kind of reminds me of something. Let's talk about magnets. Magnets are like kind of like gravity. Remember, if you bring a nail close to a magnet, then it's going to be attracted to the magnet. The nail is going to be attracted to the magnet, and secretly, the magnet is going to be attracted to the nail as well, because for every action there is an equal opposite reaction. They are action-reaction pairs. But in short, they are going to be really attracted to each other the closer you bring them together. It's the same case with gravity. If the objects are close together, then the gravitational pull is higher. If the objects are far away, the gravitational pull is lower. The further away you are from an object, the less attracted you are to it. Absence does really make the heart grow fonder. Right, so, a bit of a joke there. Um, if the planet was closer to the sun, it would feel that gravitational attraction would certainly be a lot more than if the planet was further away from the sun. Okay, so if I take this example here, so here's a planet, here's another planet, and they are both relatively the same mass. Which one has more gravity? Is it planet 1 or planet 2? Planet 2 has more gravity. Okay, but what about if I make this interesting? I have two planets here, and I have planet 3 and planet 1. So I've got planet 3 now. Which planet out of 1 and 3, out of those two, out of 1 and 3, which planet has more gravitational pull towards the sun? And it's going to be planet 3. Why is that? Because it has more mass. It has more mass. So planet 2 is closer to the sun, and because it's closer, it has higher gravitational pull compared to planet 1. But if we're talking about planet 1 and planet 1 is smaller than planet 3 and therefore has less gravitational pull. Okay, I hope that makes sense. Let's move on. How do you calculate net force? So I'm going to draw another planet. Well, this kind of looks like the moon, and I'm going to draw different size craters. Here we are, and over here we've got forces acting on it. I'm just going to have these, these imaginary forces acting on this object. So I've got 5,000 newtons acting down, 5,000 newtons acting up, 3,000 newtons acting from the right side, and it turns out we've got about 2,000 newtons acting from the left side. How do I calculate the overall net force? Well, these two cancel each other. Why is that? Because they're equal and opposite. What about these two? What about this guy and this guy? What happens to them? Do they cancel each other? I'm going to use red, even though I don't like it. No, because we've got 3,000 on this side, we've got 2,000 on this side. We're still left with 1,000 newtons on this side. Well, that 1,000 newtons turns out that's what we call a net force. Basically, a net force is the overall leftover force. It's the one force that's left over that acts on the object. So in this case, the net force is 1,000 newtons. We'll do another example as well, just so you get it. Here's an object. We've got 10 newtons acting this way. We've got 5 newtons acting this way, and 3 newtons acting this way. What is the overall net force? We've got 8 on this side. So overall we've got 8 on this side, and we've got 10 on this side. What happens is we're left with 2 newtons to the right. 2 newtons to the right. That is the overall net force in this example. Let's talk about gravitational force. So this is just like similar to the example that I just said earlier. I'm going to use my highlighter. I'm going to add some color to this because I just love coloring. I don't know if you guys like coloring, but I like coloring and I like art. It's kind of relaxing. So the sun is kind of yellowy and it's got all these solar rays sticking out of it. and we've got some random planets and such. Okay, enough of that, because I want to keep this video short and sweet. Let's have a look. So here we've got different sized planets, and what is happening here? Which planet has a high gravitational pull? So this one is close, so it's got a high gravitational pull compared to this one here. Okay, so if we look at those two, they are the same size, the same mass, shall we say the same mass, but obviously this one being closer has a much higher gravitational pull. What about if I have two planets here, like, okay, if we go next to the Earth and I draw another planet, which of these two, the Earth or this blue planet that I just drew, will have a bigger gravitational pull? It's the Earth. Why is that? Because it's more massive, it has more mass, okay? So two things that affect the gravitational pull between the objects. It is the distance and the mass, okay? Moving on. Let's calculate the net force acting on this box. So there's another example like the one we just did. If I want you to look here, there's 45 newtons weight acting downward, and there's a normal force of 45 newtons. Now we don't need to label those actually. So these two cancel. There's nothing in the vertical or the y-axis in the vertical direction. What about in the horizontal direction? We've got a person pulling here, and this person is pulling with a force of 15 newtons, okay, while this person over here is pulling with a force of 45 newtons. So what happens in this case? Do they cancel each other out? No. This person is pulling with a much higher force. So it turns out there is an overall force now of 13 newtons towards the left. And it's very important that you understand that forces are vectors, which means they have a magnitude, a size, and a direction. So it's going to be 30 newtons to the left. That is the overall force. Okay, I hope that was good. I hope that was easy. Please make sure that you watch the video again if you don't understand anything, and make sure you go through the exercises in your book and the notes. And I would like to say happy Ramadan and happy Girgaan, because we are coming towards the 3 days of Girgaan. Very interesting event. And please make sure that you continue with your Siyam and Qiyam, and may Allah accept our Siyam and Qiyam. Take care. Over and out. Share, like, and shufkum ala khair. Assalamu alaikum.